Now we're looking at 10.3 notes, part 2. We're going to use combinations and permutations along with the fundamental counting principle, because the problems here are going to require more than one method. So if we recap, if there is repetition, then you must use fundamental counting principle. If there is no repetition, and order is important, order matters, if you change things around, you get something different, then you may use permutations or fundamental counting principle. If there is no repetition and order is not important, meaning if you move items around it's really no different than how it was before, then you must use combinations. I would suggest on these problems you ask yourself a series of questions. 1, how many parts is the job? 2, does order matter in this job? And 3, is repetition allowed in this job? So question 1 says that there are 7 women and 5 men. A committee of 3 women and 2 men is to be chosen. So there are 2 tasks to this job because I have to pick a set number of women and a set number of men. Now each of these will use combinations because I'm forming a committee overall where order doesn't matter. So I have 7 women and I need 3. Times 5 men, I need 2. This is times, remember, because the fundamental counting principle says you multiply together the number of parts that you decided you needed. Again, this is all calculator work to get to 350. Alright, so in a Super Lotto Plus, we're going to say that in the California State Lottery game, you select 5 distinct numbers from 1 to 47. That means they're all different. And then you choose one mega number from a different pool of numbers 1 to 27. So how many different sets of 6 numbers can you select? Well, this is a 2-part task because you're choosing 5 numbers from the first set and 1 number from a different set. Now when you play the lotto, order doesn't matter. The clerk at the gas station is going to print your ticket in numerical order, even if you told him differently. So the first 47 numbers, I need any 5 because it said they had to be distinct. Of the other 27, I need 1. So I'm going to multiply that together and see I have a very large way of getting an answer, meaning it's very hard to win at the lottery because these are all the possibilities and only one ticket will win. Now let's change it a little bit. Let's add a condition. So Eileen Burke walks into the gas station and she tells the clerk her age. She tells the clerk her husband's age. Then she picks any 3 remaining numbers from the first set, and then she still has to pick her mega number. So this is actually a 4-part task because she tells the clerk her age. Now the reason why that's a 1 is because we all have a set defined age. Her husband's age is a different number, and then of the 47 numbers there are 45 left and we need 3. The mega number is separate of all of that and there are 27 choices. Finding all that with our calculator, we get to our answer. Now let's go back to those 5-card poker hands, and let's say we want to have only cards of a single suit. Well, let's just drill that down and say, what if we needed 5 cards that were all diamonds? Well, there's 13 diamonds, and I need 5 of them. Remember, every time we play poker, it's a combination. I cannot repeat cards in my hand, but order doesn't matter. So I get 1287. Now I'm multiplying it by 4 because there's 4 total suits. The next one is call signs for a radio station. It says that in the United States, call letters begin with K or W. And then they have 3 letters total. Assuming no repetition of letters, how many 3-letter sets are possible? Well, I'm going to make it a 3-part task and just plain and simply use fundamental counting principle. The first number must be K or W. The next 2 numbers cannot repeat. In fact, all 3 can't repeat. So K or W goes first, And now I have 25 letters left because the K or the W is out. And then I have 24 left for the third position. 5 says that we want to know how many total games will be played in basketball if each team in an 8-team basketball league is to play each other team 3 times. Well, let's just say, how many times can 2 teams play each other? Well, order doesn't matter how they walk out on the court. A team plays B team is the same as B team playing A team. So 8 teams, I need 2 to have a basketball game. So that would be 28. And that would be if they only played each other once. So we're going to multiply by 3 because they're playing each other 3 times. Now let's get back to those 5-card poker hands. So let's say I want 4 clubs and 1 non-club. I'm going to use the fundamental counting principle to break that into 2 parts because I have to guarantee a certain number of clubs. Now there are 13 clubs in a deck. Remember, every time you deal with poker hands, you're going to use combination because order doesn't matter and repeats aren't allowed. So 13C4 would get me my 4 clubs times there are 39 other cards in the deck because there are 52 total cards. So if 13 are clubs, 39 are not. So any of those 39 would finish me for 1 non-club. Let's say 2 face cards and 3 non-face cards. Well, first let's review. A face card is a jack, a queen, or a king. So there are 12 of those in a deck. I need 2. Times 40 other cards that are not face cards. I need 3. The reason why I can't have 5 dashes and just do 12 times 11 and then 40 times 39 times 38 is because that assigns order. And I cannot assign order when I am playing poker. How about 2 red, 2 clubs, and a spade? Well, there are 26 red, take 2. There are 13 clubs, take 2, and there are 13 spades. You could write 13C1 here, but that's the same as 13. Use your calculator to get to your answer. Now let's look at all the ways that we can arrange 8 girls and 7 boys to put on a recital. The key word is arranging here, which means order definitely matters. If you go first, or you go 5th, or you go 8th, that's all different. So let's say the girls must perform first. So there's many ways to do this. You could do 8 girls P8. That means that you are assigning order to 8 girls. Times 7 boys, assign 7 boys order. Or you could do factorials. You could say line up all the girls, then line up all the boys. So 8 factorial times 7 factorial. Both will get you the answer. Now let's say that a girl must perform first and a boy must perform last. Well, there's 8 girls to go first, and there are 7 boys to go last. I'm going to think about those pieces first, and then I'm going to put everybody between. Well, there are 13 people still that need to go. I need to assign order to all 13. Let's specifically say now that it's Elisa and Doug that must perform first and last respectively. So how's that change our work from B? Well, instead of any 8 girls going first, now there's only 1. And instead of 7 boys going last, there's only 1. There are still 13 people in the middle that must all be assigned order. D says the first, 8th, and 15th performers must be girls. So I'm going to make it 4 parts. I'm going to say first person must be a girl, 8th person must be a girl, 15th person must be a girl. Remember, once you go, you don't go again, so that's 8, 7, 6. Now that's 3 positions we've already thought of. So there's 12 left because there's 15 total kids in the recital, and I need to assign order to all 12. Now let's just take a step back and do an easier problem. Make sure we're not losing our footing. Let's just simply say Sean takes 2 pair of shoes, 5 pants, and 6 shirts on a trip. Let's say everything goes together. How many outfits can he wear? Well, this is straight up fundamental counting principle. 2 times 5 times 6 would give him a total of 60 outfits. 9. Taking a step back and realizing that not all problems require multiple steps. Suppose that an experiment consists of tossing a coin 10 times. Find the number of ways of obtaining exactly 4 heads. Well, there are 10 tosses, and you want to see something 4 times. I don't care when it happens, and you can't repeat. Each toss is unique, so 10 see 4.